This is a short talk on compressing graphs and indices with recursive graph bisection. A common problem in modern systems is to store a mapping between an entity and other related entities. For example, consider a system that serves adjacency information in an online social network. Given the underlying friendship graph, we might want to know who the friends of a user are in the network. This requires storing for every user an adjacency list of the IDs of its friends. As another example, consider a search retrieval system. Given a set of documents, it calculates an inverted index, which is just a map from words or terms to the documents that contain them. Again, the system stores for each term an adjacency list of the IDs of the documents that contain that term. Usually the graphs that we deal with have orders of magnitude more edges than vertices. In such graphs, many vertices can have long adjacency lists. By compressing these lists, we can lower the storage footprint of our graph or inverse index. Suppose we want to compress an inverted index where documents and terms have unique identifiers in separate spaces. For each term, we store a set of documents that contain the term. A common technique for compressing these sets is to sort them, calculate differences between consecutive IDs, and then compress the differences using an integer compression technique suited for small numbers, such as varint or Elias-Fano coding. However, we can improve the compression if we reassign all the document IDs in a way that makes documents containing the same term have similar IDs. Here are the documents after reordering. The differences produced are smaller and require significantly less space to store. How do we find compression-friendly orderings? Suppose we want to reorder this graph. One way to solve this problem is to first bisect or partition the graph into two roughly equal-sized pieces, and then recursively solve the problem on each piece. The orders recursively computed for each piece are then just mapped to the contiguous parts of the order. How do we find a bisection of the graph that is good for compression? More generally, suppose we are given a bipartite graph of query and data vertices, where we want to reorder the data vertices so that query vertex adjacency lists are easily compressed. One way is to randomly initialize the bisection. While we haven't converged, we can then swap vertices which improve our optimization goal, as so. By making our optimization goal reflect the cost of representing the graph using delta encoding, the algorithm produces a compression-friendly bisection. The last piece of the algorithm is to run the bisection method recursively. We take the final bisection tree and lay it out onto the line to produce the final ordering of the vertices. In summary, we give an algorithm for computing compression-friendly orders of graphs and indices. In the paper, we give a unified model for graph compression that captures both graph reordering and index reordering. We show that the underlying optimization problem that minimizes the number of bits in this manner is NP-hard. We show that our algorithm is highly scalable, running in just a few hours on billion vertex graphs. It also consistently outperforms the state-of-the-art in graph reordering and index compression. Please see our paper for more details.